For counting. This section requires much greater use of formulas as we consider 5 different methods for counting the number of possible outcomes in a variety of situations. Not all counting problems can be solved with these 5 methods, but they do provide a strong foundation. Multiplication counting rule. Sometimes this is called fundamental counting principle. For a sequence of events in which the first event can occur in N1 ways, the second event can occur in 2 ways, the third event can occur in 3 ways, and so on. The total number of outcomes is this times this times this, all right? I like to call it a blanks problem. So sometimes I'll call it a blanks problem. And you're just taking the number of ways to do this times the number of ways to do this times the number of ways to do this, and so on and so on. So if you had like 4 shirts and 3 pairs of pants and 5 pairs of shoes, and that was your wardrobe, and somebody said, well, how many different ways are there for you to pick one of each for an outfit to wear? Well, you'd just say 4 times 3 times 5. What is that, 60? There would be 60 ways. I call that a blanks problem. There's a blank for each of the different things that you're talking about there. Okay. One thing to consider is a lot of the times you're going to see the word and. When you see the word and we've talked about this before, a lot of the times the word and implies we're going to multiply. We've talked about the word or, and we add when we see the word or, and we multiply when we see the word and. Factorial rule. The number of different arrangements, order matters, of n different items when all n of them are selected is n factorial. So if I did like 4 factorial, you should find where it is on your calculator. It's the exclamation point button. Mine is over here. 4 factorial. Find yours on your calculator. If you have a TI graphing calculator, you go inside the math menu, arrow over to PRB for probability. It's inside there. Other calculators, it's probably going to be similar to mine, I think. It might be a math menu or a probability menu, but check it out. 4 factorial. 4 factorial is like this. 4 times 3 times 2 times 1. And it equals 24. But we can kind of think of it as a blanks problem. But a factorial, 4 times 3 times 2 times 1. Number 1, multiplication counting rule, hacker guessing a passcode. When making random guesses for an unknown 4-digit passcode, each digit can be 0 through 9. What's the total number of different possible passcodes? So to me, this feels like a blanks problem. There's 4 numbers that you would have to guess if you were guessing someone's passcode. Try and get in their phone. It has 4 digits, and before Face ID, that's what they used. But you would have 10 different number choices to guess for the first number. Then for the second number, you kind of have to think about an idea of whether the number can repeat or not. And in this example, it doesn't say that it can't. So I suppose I would still have 10 choices here. I would have 10 choices for each of those 4 blanks in the passcode, because we could repeat. My passcode might be 1111. All right, might be 9999. Okay, could repeat, doesn't have to. You multiply that out, that's 10 to the 4th, or 10,000. Given that all of the guesses have the same chance of being correct, what's the probability of guessing the correct passcode? So we're finding the probability of guessing it correctly on the first try. So if you think about it, if you're trying to break into my phone, how many passcodes work on my phone? Just 1, right? Okay, and so think about probability. We always think about probability as part over total. There's one way of choosing the right number out of the 10,000 or so, well, the 10,000 numbers. So 1 over 10,000 is 0.0001. Okay. A lot of the problems kind of act like this. Number 2. A statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies. A. How many different travel itineraries are possible? One technique that we can do if we don't know what to do is draw a picture, make a list, something like that. And so how many different travel itineraries are possible? Well, let's try to start a list. You might go to Gallup, then Nielsen, then Harris, then Pew, then Zogby. Or you might go to Gallup, then Harris, then Nielsen, then Pew, then Zogby. Or you go to Gallup, then Pew, then, okay, this is not going to be realistic. I don't want to list all these out. Okay, right? I could list them all out, but it's going to take me forever and I don't want to. Okay, to me, this looks like a blanks question. I've got 5 different places to go. So I'm going to have 5 different blanks. It's a fundamental counting principle. Okay. So if you think about it, you're like, well, how many choices would I have for that first blank or that first location? 5. So you pick one and you go there. And after you go there, how many choices would you have for the next one? 4. And then the next one. And then the next one. And then the next one. 5 times 4 times 3 times 2 times 1. We could calculate that. All right. Or, this problem is called a factorial rule. I'm not sure I would have recognized that as a factorial until after I saw that, but it is. 5 times 4 times 3 times 2 times 1 is a factorial. Either way, you're going to get 120. 120 different ways of doing that. Okay, would you have wanted to list all of those out? Not me. Part B says, if the itinerary is randomly selected, what's the probability that the presidents are visited in order from youngest to oldest? So probability, young to old. How many ways are there of listing them out from youngest to oldest? There's only one way to do that, right? And so since probability is part over total, it's going to be 1 over 120. Now, sometimes it's better to do the fraction and sometimes it's better to do the decimal. And so in general, my rule is which one's easier to talk about, which one's easier to write. And sometimes it's hard to tell, but we might want to look at the fraction as the answer. We might want an exact number, or we might want to round off. It's probably easier on your brain to understand how small this number is if you look at the decimal. But the fraction's good because it's exact. Now, this is kind of a hard couple of paragraphs to read, I think. I need you to read it on your own. I don't think you're going to get anything out of it if I just read this to you. So read through this on your own and try really hard to understand what they're talking about. I'll try to break it down. We're talking about permutations and combinations. And I think a good way to think about this is a group from a group. A group from a group. If you've got a group of 8 items and you're going to pick 3 of those 8 items, that's a group from a group. Okay, 3 out of 8. So anyway, that's what I'm looking at. Permutation has its own formula here, NPR, and for that, for a permutation, make sure you understand that order matters for a permutation. Okay. When we talk about a combination, order does not matter. So back in my day, we had to use this formula, and I don't know why they didn't want us to use the calculator, but I'm gonna let you guys use that calculator. So find where NPR, NCR, find your permutations and combinations on your calculator. That's what we're gonna use. If you don't use that, you can always fall back on these formulas. But these formulas are harder than they need to be, I think. Okay. So to me, again, the hardest part sometimes in these problems is just figuring out what type of problem it is. And so that's why I like to ask myself this question. I start a problem and then I'll say, am I talking about a group from a larger group? Yes or no? All right. And if it is, if I am talking about a group from a larger group, then I ask myself another question, does order matter? And if order matters, then it's a permutation. If order doesn't matter, it's a combination. Okay. But we go back. If it was not a group from a larger group, if it's not a group from a larger group, then it's probably going to be fundamental counting principle, the blanks problem. So this is a good way of thinking about it. Always start with, is this a group from a larger group? No. Fundamental counting principle. Yes. Permutation or combination, depending on if order matters. Example 3. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third, and you must select them in the correct order. The 140th running of the Kentucky Derby had a field of 19 horses. Part A says how many different trifecta bets are possible. So the way I like to attack this question is I like to say, well, is this question talking about a group out of a group? Do I want a group of items out of a larger group of items? And I think it's pretty easy to see that yes, it is. Okay, the next obvious question would be how many out of how many? You're taking 3 out of 19, right? In this example. So the question becomes, does order matter or not? Well, they tell you right here, you must put them in the correct order. So yes, it does. And so this is going to be a permutation. We're taking 3 items out of the 19 items and putting them in order, first, second, third. So I don't really want to use that formula from above. Feel free to. I'm going to use my calculator and say 19p3. I recommend you try it on your calculator. I get 5,814. Part B, if a bettor randomly selects 3 of those horses for a trifecta bet, what is the probability of winning by selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third as they did? So sometimes these problems seem a lot more confusing or a lot more difficult than they actually are. There's only one way to win. Okay, there's one way to pick the right 3 horses in the right order out of, we just calculated the total number of ways to have 3 horses in order out of 19. So the fraction 1 over 5,814 or the decimal 0.000172 kind of depends on how accurate you want to be. Do you want to be exact? Do you want to be about? Something like that. So then the last part of this question says, do all of the different possible trifecta bets have the same chance of winning? And that's kind of a tricky question, I suppose. Does anybody think they can answer that? Okay, think about March Madness coming up. All right. If we have 64 teams in the tournament, forget about the extra 4 or whatever. 64 teams in the tournament, and we're gonna pick 4 to finish in the final 4. All right. So if there are 64 teams, and I'm gonna pick 4, I don't care what order it is. That's going to be in the final 4. There's that many different ways I can pick 4 teams. Okay. 635,000 or so different ways of picking 4 teams out of the 64. All right. Does it matter which 4 teams I pick if we're betting money on it? Don't you think you'd want to pick like Gonzaga and Arizona and who else would be good? Auburn and Duke. Okay. Those 4 teams have a lot better shot than maybe Notre Dame and Indiana and St. Mary's and whoever else. Okay. So do they have the same chance of winning? Well, no. Some of the horses are going to be favored. Some of the horses are going to be better than the other horses, and usually they'll give you odds before you bet. Number 4, lottery. In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order does not make a difference. Part A says, how many different lottery tickets are possible? Try to write down the answer to this before I do. Okay? How many different lottery tickets are possible? So again, I'm going to ask myself, am I taking a group out of a group? And clearly I am. I want 5 out of 39, so the question becomes, does order matter or not? And they told me right there, order does not make a difference. So this one is going to be a combination. 39, C5. Five, 7, 5, 7, 5, 7. Part B, find the probability of winning the jackpot. Well, there's only one way of winning. You got to have the right number. So it's going to be 1 over 5, 7, 5, 7, 5, 7. Part over total, probability. You know, it's kind of tricky sometimes because you have to pay attention to what the question's saying. Do they want to know how many ways, or do they want to know the probability? And that's what we've just done in some of these problems. How many ways? What's the probability? All right. Permutations rule with identical items. Some of you that have had my class before might remember the word indistinguishable. The number of different permutations, order counts, when n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows. Now, I know this formula looks really complicated, but it's a lot easier than it looks. I call it the Mississippi problem, and problem number 5 is going to use that formula. Problem 5 says, how many different ways are there of shuffling the letters in each word? So part A says fork, and notice there are 4 letters. You can think of it as a blanks problem. There's 4 ways to fill in the first letter, then 3, then 2, whoops, then 1. It's going to be 4 factorial, or 24. There are 24 ways of shuffling those letters in the word fork. Okay. Part B, food. It seems like it's going to be the same thing, but check it out. If you look at those 2 O's, and if you switch some spots, nobody would ever know the difference. Okay. So we can't count OO and switched around OO as 2 different things. We've got to, those O's are exactly alike. They are identical. They are indistinguishable from each other. So what we're going to do is we're going to say, well, if all 4 of those letters were different, it would be 4 factorial, like fork was. But what we're going to do is we're going to divide by the number of ways of shuffling those O's. Okay, of switching those O's back and forth. So in this case, we're going to divide by 2 factorial. 4 factorial divided by 2 factorial is 12. There are 12 ways of shuffling those letters in food so that you can tell a difference. Okay. Now, I like the word Mississippi because I think it really does a good job of illustrating this problem. That's why I call it the Mississippi problem. Okay, we're going to do the same thing. How many letters are there in Mississippi? I see 11. There are 11 letters in Mississippi, and if they were all different, this answer would be 11 factorial. If they were all different, okay? But they're not. And so you look at those S's, and we would be able to shuffle those S's and nobody would be able to tell. We'd be able to do the same with the I's and the P's, okay? So what we're going to do is we're going to divide by 4 factorial, which is the number of ways of shuffling those S's, and another 4 factorial, which is the number of ways of shuffling those I's, and a 2 factorial, which is the number of ways of shuffling those P's. Okay, anything that repeats, anything that's exactly alike or identical, you're going to have to divide off. Now, You need to be really, really careful on your calculator, because most calculators, if you don't put parentheses right here when you type it in, it's going to mess up your order of operations. Okay, so this one actually works properly, but most other ones do not. So I'm going to do 11 factorial divided by parentheses 4 factorial 4 factorial 2 factorial. The correct answer is 34,650. If you got like 79 million or something, you're off. Okay, it has to do with order of operations. 34,650. Number 6, designing surveys. For one survey with 10 questions, 2 of the questions are identical to each other and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Okay, seems like a tough question. All right, I remember when I was in your position, when I was in college, I had a similar question like this on a test, and I still remember that question. I missed it. It was like fruit in a basket or something like that. Okay, I wish I had thought to make it into the Mississippi question, because that's all this is. All right, there are 10 letters, right? Or 10 questions. So 10 letters in this word. What I'm going to do is I'm going to say, all right, 2 of the questions are identical. So let's call that capital Q, capital Q. Try really hard to make those identical. You've got identical Qs. And then you've got 3 other questions that are also identical. So let's say lowercase q. Those 3 Qs are identical. Then since there are 10 questions, we must have 5 other questions. So let's just say A, B, C, and D, and E. So I just made this question from something completely unrelated into the Mississippi problem. I've got a word, 2 of the letters are identical and 3 of the letters are identical. I want to know how many ways of shuffling those letters. It's the same question. So I see 10 total, right? If all 10 of those questions were different, then that answer would be 10 factorial. But since some of them are identical, I'm going to shuffle the ways of switching those things around. So those capital Q's, since those 2 are identical, I'm going to divide by 2 factorial. And since there are 3 identical, I'm going to divide by that. 10 factorial over 2 factorial, 3 factorial. Again, when you do this division, your calculator is most likely going to need parentheses around that denominator. 2 factorial, 3 factorial, close it. 302,400.